Alright, so today we're gonna get into chapter 5. It is encouraged that you study, okay? Make sure that you study, not just reading. Studying is you have to read and think with it. And of course you should read the book. You should read right now we're giving you the book because a lot of the students can't afford the textbook. So make sure you get into this and also listen to what I am lecturing. Of course, I understand that your comfort zone is to come to school and listen to the lecture for 45 minutes, but that type of method it isn't very effective unless the student back up for 3 hours to every 1 hour lecture. So make sure that we are giving you this lecture 24/7 access to you because we believe in giving the open source material to the student is going to help them study and also to get a lecture all the time with them so they can go back and listen whenever they want to. Alright, so today we're going to get into Newtonian mechanics. And of course, the very first subsection for this chapter is we will get into particle Newtonian mechanics. Again, in science, we make things very, very simple and easy. So there are so many different objects, of course, in the world that we know, the human, that we know. But we will divide it into particle and rigid bodies, and here we break down these objects into these two big categories to analyze the motion that they do, and we call that the mechanics. And in that we have statics, and then of course the motion part is your dynamics. So for equilibrium, if a particle or the rigid body is stayed in equilibrium, that means that you do not have the external forces on it, so the motion cannot happen. Dynamic cannot happen. But as soon as you have some form of force, and of course your energy is gonna be applied to the force, and the force is going to induce the motion in the particle or the rigid body. So right now we'll get into this section of the dynamics, and we will look into the particle Newtonian mechanics. Okay, so review of your kinetics. In kinetics, so we're analyzing forces, or torques, forces that cause the motion. For kinematics, again, I'm telling you again and again, for kinematics, it's going to describe the motion without considering forces. For kinetics, in your brain, you got to think about the forces that cause the motion. When we go to kinematics, we're just going to do describing that motion without the forces. All right. So here is a little questions. Do you remember the difference between kinematics and kinetics? And here is our usual diagram. The one right here on this side showing you the velocity. Of course, this is a function of time because everything that we study the aspects of motion, we're studying against with measurement of the time. Time itself is a measurement. Anyway, we're looking at their activity in an interval of time. So here you can see the acceleration, looking at the velocity over time. And we have the velocity, and here is your object with a mass, and this is just describing the motion. So every time you describe the motion without considering the force, like here in this, we call it kinematics. Here in this diagram, look at this, there's no velocity, there's no acceleration. Of course, we are focusing here only on the force. See, this little red arrow is showing you the force. Alright, and this force is applied to this mass object here. Mass means, oh, it is an object. It can be a particle, or here in this case, it's a solid, yeah, object, which is a rigid body. And of course, in this side diagram is showing you the kinetics, okay, because we are analyzing the forces here. This description of the motion, and we describe the motion in terms of the object and then your velocity. Of course, every time you show there's a blue arrow, the object is taking from one location to the to the another, and there it generates the velocity and the acceleration. Okay, so make sure you you have this information in your head. And here in this diagram, we reveal the answer. So describing the motion with velocity, acceleration, kinematics. Here describing the forces that cause that motion, kinetics. Of course, here we're reviewing again formally. So kinetics is the study of how forces relate to motion. So a student comes to school, and your duty is to study. Our duty in academic is to continue our scholarship, and we are studying, okay, everything that we have, including us, and in many different subjects. So we're studying about us, okay, and our ultimate ambition is not just to get a job, but to, if you really think about it, doesn't matter what ambition you have, how small they are, how big they are, the ultimate ambition is to survive. To survive as a human species, as your single life, okay, my life, or life as a community, or life, okay, of the country, or even the entire world, whatever that is. Even though you try to get a job to get some money, if you really sit down and think about it, your ambition is not to become a millionaire, billionaire, or a person with a position. That's just what we do every day. But the ultimate ambition is to survive. We go out in the space to explore because we know our planet has limited life. So we try to explore as much space we know outside in the space. So and again, why do we do that? Because we have a hope, as a human civilization, to have a new civilization, new space, more space to survive again. Because this environment one day will not be stable, will not be useful, or will not be habitable. Therefore, it is important for us to explore more habitable planets out in the space, which is very, very important, starting from about 30 years ago into the future. So anyway, so again, we study because we need to know everything. Therefore, we can support our survivability, okay? So anyway, so kinetics is the study again of how forces relate to motion. So our concentration in kinetics, again, if you get this word force, I'll be very happy. Okay, and then we have a method of analysis. So how do we study that? So we study that by doing three things. One is Newtonian mechanics. The second one is work and energy, and the last one is your impulse and momentum. So these are the method. Again, method of analysis. So when you come to school, we're teaching you method of how to do things, how to apply the knowledge in order to make money, or to keep the job, or whatever, or to do the job at a company, so you can survive. So you can get money to continue to live. Anyway, so method of analysis is your Newtonian mechanics, your work and energy, your impulse and momentum, and we use these methods to study the forces, forces that cause the motion, Of course, in this section, we will get into details for the Newtonian mechanics. Of course, in Newtonian mechanics, you have to understand, the very first one is what is mass and what is weight. You have to understand the difference, yeah, between them. Then we will of course get into force, and then of course on acceleration. Yeah, so that's a review for your Newtonian mechanics, because Newton he studied these things. Okay, and because of him we know what mass is. Of course, at least we can define it. Yeah, effectively what mass, what is weight. So defining something effectively meaning we recognize the difference between, yeah, these things. So here we know what mass is and we know what weight is, and what is the difference between the two. So mass you do not have. Okay, when you think about the weight, there is a direction, you know, where this weight is going. Weight is again is a force. Okay, we usually let me see, where's my pen here. One moment. Oh my gosh. Okay, here I got my pen. So anyway, so weight is nothing but force, yeah, and weight is we're looking at the mass, yeah, and your acceleration. So this is again your acceleration due to gravity, yeah, and we usually write it this way. So this is your review. So you gotta get this in your head. Okay, so instead of a we write it in gravity, yeah, acceleration due to gravity. Even though it is acceleration, we call it gravity anyway. So now you have this. Okay, so weight is mass, and you have something more, and that is your this mass is going. Okay, if we represent weight in the form of a vector going downwards, yeah, towards the core of our planet, which is Earth. So this is your Earth, ERTH. So we have mass on, yeah, everywhere, and it is pulled down by the gravity, force of gravity, because every object, okay, and between two objects there is an attractive force between them. So your Earth and then something, yeah, on the surface of the Earth, they are attractive to each other, and of course the mass of that, okay, with the with the help of this gravity force is gonna be pulled down with this acceleration. Okay, so what's the code of that? Right here, yeah, the center of the Earth. So anyway, so in here we call it this mass is subjected to this acceleration due to gravity. Of course, there's many balance, yeah, conditions, many balance conditions for every mass, right, on this planet. And of course we totally determined that weight is nothing but a force. Okay, force usually caused by the gravity here. So anyway, a mass is, you know, when you look at it, we don't care about the acceleration subjected to it. It's just purely mass without it. Okay, so therefore you know the difference between what mass and then what is weight. Okay, so weight usually have a little vector arrow like that, mass without the arrow. Okay, and then because you know what force is, so force is something that you apply to a mass, and that mass is going to go, okay, into a motion, and we usually write it mathematically this way. Okay, mass and the acceleration that mass is going, all right, in a motion caused by that force, and we call that the force. And if you really think about physical thing, yeah, there's nothing but your physical thing is this object of interest that we're looking at. It could be a particle, or it could be the rigid body. Okay, depends on the size and shape of that particle. Usually the size is there isn't, yeah, negligible because it's so small. So anyway, so you got to understand what force is. Okay, you got to know what is the physical thing behind this word force, which is nothing but your object right there going with an acceleration in a particular motion. Yeah, so as soon as you have acceleration, it means that mass is moving. Yeah, moving in a particular direction, because acceleration is a vector. Acceleration is depending on the velocity that mass is going with, and velocity is just defining from which location to what location this mass is moving how. Yeah, so when you think about force, you got to understand about the physical thing, and that physical thing is taking position, making velocity, and having some form of acceleration, whether that's constant, average, or instantaneous. Okay, you got it. Yeah, so every time we think about the force in your brain, this gotta be automatically. Yeah, um yeah, you gotta have this everything in your brain as soon as you think about force. Okay, and then of course acceleration, then we're looking at this yeah, the aspect of the motion, because your physical thing again is yes, moving or taking from position to position, or making velocity, and every time that velocity changes, then you have some form of acceleration. Okay, whether it's going fast or slowing down. Yeah, going faster or slowing down. Okay, so anyway, so these are, all of your Newtonian mechanics review. Yeah, you really really need to understand. In order for you to understand, you have to study. Okay, this is just a break for you, and you can type this in Eureka. Yes, and then of course you can go to YouTube, because that's where all the videos are, and you can take a look at it. Okay, so this Eureka, yes, I search it for you. Yes, here is from TED Education, and it just trying to, yes, talked about the mass and weight. Yes, so Eureka is, as you know, yeah, your Archimedes principle, because he discovered the object, submerged in a fluid, or and that object is going to experience an upward buoyant force. Yeah, and that force is going to equal to the weight of the fluid displaced. Okay, so that's kind of like your middle school or high school review, yeah, for you. So this principle is going to directly link with your force, okay, which is your weight, okay, this guy right here, and of course the mass. Yeah, so mass is the property of matter, okay, and your weight, okay, proved by Archimedes. If you throw it into the water, okay, is going, so throw this mass into the water like that, and of course this water is going to spill out of that container, okay, which is equivalent to this object submerged in that fluid. Okay, so because of this upward buoyancy, which is going to be equal to the weight of that. Okay, so this is, let's say, the fluid come out of this tank, and this mass or the weight is equal to this, all right, spilled or displaced fluid, yeah, amount. So and that is a review of your Eureka, which you can see it right here in this, okay, video. Okay, if you like the animation and things like that, then you need some form of pictures or animations, so that's going to help you a little bit easier for you to understand instead of listening to the lecture. Yeah, of course we usually give this Eureka example so you can be able to understand the context of mass and weight. Yeah, and we usually link it to the Archimedes, long time ago, very very ancient fundamental contribution of the I would call him a scientist or physicist. Yeah, because he works on the fluid buoyancy and the relationship again between mass and weight. So if you understand the relationship, then you can be able to understand the force, yeah, because mass and weight they're related like this. So you have your mass, yeah, and then of course this whole thing is your weight, yeah. So you can see this is the weight and that is the mass, and its relationship is directly proportional to each other. Okay, so meaning the weight will go up if your mass is bigger, the weight will go down if your mass is small, yeah. And again, our aim is to be able to understand the mass and the weight, the difference between them. You have to understand it. Yeah, since long time ago, from ancient time, we try to understand what mass is, what weight is. Yeah, because they didn't really understand at that time. But over time, of course, many centuries passed, and now we totally understand what they are. Yeah, so knowledge is passed from one generation to another. And we are very, very lucky, all right, today. It's because we can do studying, yeah, without the threat of politics or people in power. A long time ago, they get rid of scientists, yeah, because some of the people in power cannot be able to stand the intelligence of regular people, yeah. So we're very, very lucky because now the education is about 80% supported, yeah, by the people in politics or people with money, yeah. It wasn't so long time ago. When we commonly think about the mass and weight, we think about, okay, it's something is heavy, yeah. So that's how we describe weight of something. Something is heavier, something is light, and we call it weight, yeah. For mass, in common, yeah, common words, every day we don't really talked about it. Yeah, we don't really talk about this. We usually talk, yeah, every day about weight instead of the mass, but the weight and mass is actually related. Okay, that way. Of course, eureka is just a word that we usually use it to symbolize our science, yeah, scientific discoveries, because these discoveries they have changed our understanding, yeah, of these fundamental principles. Because in physics, yeah, dynamics is a part of the physics and also a part of mathematics and a part of engineering. Of course, now new field, engineering, technology, and the distinction between the mass and then the weight, because the mass is just an intrinsic property, if we formally describe that, and then your weight is a force, all right, and totally depending on your gravity. And we have to understand the difference between the two, okay? And their very significant contribution and realization in physics and also in science, okay? Because the engineering is a part of science. So why do we have to understand what is mass and weight? Is because it's so important in physics and engineering, is because the correct identification of mass and weight is going to help us solve problems, okay, relating to force or motion or energy, because everything that we build, it depends on the force, the motion, and the energy. Everything that we do, okay, living, depends on the force, the motion, and energy, from your health, okay, from your human health all the way to all of the biggest human achievements, all right, throughout the civilization. Depends on the force, depends on the motion, and depends on the energy, okay? Of course, again, in the next slide, we're going to get into understanding of mass and weight again. So here, write it down, yeah? Your weight is, here is your mass, and here is your weight. And here is something, right, that is the aspect of the motion of this mass, which is acceleration, meaning this object, okay, with the mass moving with this much of velocity, and we call that weight. And again, you when you think about the weight, okay, you would think with me, your understanding of weight is direction is always towards the core or the center of your planet, okay? So which is Earth right now, here, yeah, our planet is like this in your head, okay? Um, then you would want to think about other directions, yeah. So if you think about other directions, we have this, mass going with an acceleration, and that direction can be like that, mass going that way or mass going this way. See like how you can see all of this, and of course these direction can be all, yeah, 0 all the way to 360-degree directions, okay? And that is happening in, again, not getting into real complex, 3x's, okay? Yeah, so that's where all of your degree of freedom of that motion come in, all of that, yeah. So here is a very complex system. If we draw it, one axis or two axis or an axis with a particular angle, then we have everything like this. And of course in engineering you have a point and the line, the surfaces, and the angles, okay? So make sure these are the fundamentals of engineering, where you got to understand, if you think about a mass in the space, you are analyzing that mass or the movement of that mass or the motion of that mass in axis, 3 of them, 6 directions, major directions. You also have each axis has a 360-degree, okay, angles that you can take. So that's pretty complex system, and that's why we have many different coordinate systems that we use to analyze the motion, complex or relative, yeah, motions. And of course, mass is a scalar because we do not think about the direction. The weight, we have acceleration to think about, so therefore it is a vector. And you have again, yeah, direction that way, this way for one axis, another axis like this, of course, and then another one right there. And of course, we also consider the direction if you combined all of the axes again, yeah? So your Newton's second law is going to use the mass, but not weight. So here, this is just a name of what he found, yeah, about this principle. So the guy who found about the this law or the principle theory is Newton long time ago, and he found 4 of them actually. So this is a second one, yeah? So second one is this: your weight is equal to the mass time acceleration of some sort. This can be acceleration, deceleration, because acceleration has a 2 direction if we consider the acceleration on an axis. Yeah, if we consider the acceleration in a different axis, then we have a very complex, okay, directions that we need to pay attention by using different angles in between these axes, okay? So here we go. So second law is going to use the mass, not the weight, which is this guy right there. Newton's second law, yeah? It's the mass. Because mass is very important, because without the mass, a physical thing, or matter, it's impossible for us to analyze the motion of that object, okay? Without the mass, it would be a particle, sizeless particle, and it's very difficult, for, in terms of Newtonian mechanics, for us to analyze or study that motion. But of course we can go up to a certain mass, yeah? It can be very, very small, and it can also be very, very big. Again, mass is a scalar, weight is a vector. Newton's second law, we're going to use the mass and not the weight, okay? Which is this guy right there, right? And your weight is on this side, yeah, which is force actually. So every time you think about the weight, you've got to know weight is a force, okay? And of course, depending on the gravity, and we call this acceleration due to gravity, not whatever acceleration, but it is a particular acceleration that depends on the environment that we are living in, okay, which is your planet. Of course, there are some cartoons here and to refresh your mind. And of course, this example is asking you to identify whether or not the number given next to the objects is specifying mass or weight. So here is the number given next to the object. So the first object is your apple. The number given next to it is 182 gram. Yeah, and we're gonna look at this number, and we have to identify whether or not this number is mass or weight. So when you look at it, you can see the unit, and that is a gram. Yeah, so therefore that's a mass. And here is a unit. Yeah, kilo here, and then you have Newton. So therefore that's a weight. And here pound, weight. Here ounces. Okay, is going to be weight. Yeah, here kilogram, mass, and here slugs is going to be your mass. Yeah, of course we go to the next to reveal the answer, and you can be able to see this. Okay. I know that some of the students are not listening to the lecture, and it's very contradicting the way that they think. So you would listen to the lecture if I give you the lecture in class, but you wouldn't if I don't give you the lecture in class. Why? I'm the same individual. Getting the lectures online is, in fact, better for you because you got me all the time. Yeah, you can always go back and adjust how you want to listen a little bit, like 10 minutes a day or 10 minutes in an hour, and come back to it, and you can do whatever you want to do either as you listen. Yeah, we traditionally we give the lecture in class, and that was all long time ago stuff. Yeah, there are 20 to 30 years ago. Of course, some of the professors still practice it, but it's not effective because the student got to put about 3 hours, per hour of lecture in class, and you also have to take notes. So these are the old methods that we use, and it wasn't very effective. And some, very very hard professor we even record, their lectures, but not anymore because nowadays about 80% of the professors, modern professor, we record it for you. Yeah, so therefore you have it with you. So anyway, so it is better that we go, we change ourselves, on these progressions. In education, we call this education technology. Okay, which is actually enforced to the school, to the professors and teachers and the students. Yeah, so make sure, of course, we all of us have the inertia, because even education is a accumulated motion. Yeah, if you really think about it in physics. So we want to do the way that we do and keep ourselves in our comfort zone, but make sure that you grow with the world. You grow with the technology, because at one point in the very near future, everything is going to change. And that again is because our ultimate goal is survivability of the human civilization and species. Yeah, and we are very our species is very dependent on the environment, and we have a very delicate and limited range that we can survive. Okay, so therefore we have to study, faster and than we had ever done. From civilization to civilization, because we realize that we got to get this knowledge and we got to get it fast. Okay, so younger generation got to actually start to learn the code from elementary school, so that they can be able to grasp everything in a fastest rate. And again, you need it because the robotic era is initiating now, where we use the artificial, which is a machine, intelligence, because human intelligence is not enough anymore. Our brain is not enough. Okay, so we need a combined brain, stored and systematically stored artificial brain, for us to be able to understand almost everything, so we can manipulate our environment to support the survivability of human civilization and species. Okay, so in many different universities all over the world, you will hear this, this message, okay, again and again, because all the professors in different areas are obligated to give you this message to the next civilization. Okay, all right. So here are the answer, your mass. Okay, and I am going to circle this for you. Weight, pay attention to the pound, of course. And here is the one thing that a lot of the students make mistake. They always think ounce, okay, is the mass, but no, it is your weight, okay, and your kilogram, and then of course your slug. Depends on the unit system that we do. All right, and then the next one is your conceptual example. So 5.1-2. So here we are thinking about astronauts, and they are on the moon, and of course they can jump higher, than on the Earth. So if you jump about this on the Earth, okay, and you can be able to jump higher, okay, on the moon. All right, the same, of course, the same people. So you have to analyze, okay, why? Okay, is it because they weigh less on the moon, or is it because they have less mass on the moon, or is it because there is no atmosphere on the moon? So now we are in in mass and weight. Okay, we're trying to understand the difference between the two, and now we change the planet, which is the Earth, and then your moon. So your moon has a very small mass compared to your Earth, because your Earth is bigger. So I should draw like this, the Earth, and then the moon like that. So therefore, when you're the same person here, and you're here, and you jump, and you reach a height on the Earth, but you jump, and then the same mass your body is, and you get to the higher height on the moon, is because you weigh less on the moon. Why? Because of this gravity. Here the gravity of the moon. So when you compare the gravity, because your weight depends on that acceleration due to gravity. So when you think about it, right? So this is the Earth gravity is bigger than the moon gravity. So therefore, it is going to pull your body down, okay, with a bigger force. So therefore, you're going to come down, okay, your mass with a velocity, and then your acceleration depends on that velocity, pointing towards the core of the Earth. So anyway, so this is your weight, okay, and here you can go up higher, higher is because this gravity is small. So therefore it's going to pull you down with a smaller force. So therefore you weigh less on the moon, so meaning the force, okay, is equal to the mass, which is the astronaut mass, and then this is the acceleration due to the moon, okay, which is going to be like this. So this weight is less, okay. So I would just say the weight, okay, on the moon is actually smaller than the weight, okay, on the Earth. Of course, you usually write it with the W symbol, so we can just write it E here and then W symbol with the little m right there, okay. So when you think about that weight, okay, is actually less, than your weight on the Earth. All right. Okay, so the answer is this one. Okay, so here, of course, we show you a little nicer slide, so you can see the answer clearly. All right, another one is, so this guy, I know, so astronaut, another example, you're floating weightlessly, okay, in the space. You're weightless because you have nothing, pulling you down. So therefore, in the space, you're weightless because you don't have gravity force in it. There's no gravity in the space. So therefore, you have weightlessness in there, and then and that person is going to shake the wrench. Okay, so here is you, and then you're shaking the wrench in his hand back and forth, right? And you're shaking it in the hand back and forth. So now we have to consider this three conditions right there for this problem. So the very first one is the shaking requires no effort because the wrench has no inertia to resist the motion. that isn't true right away, because every time you have a force, then you have, something to resist the motion, because your wrench has the mass. And then the shaking requires some effort, but less than one, or less than on Earth, because the wrench weighs less in space. Yeah. But it doesn't say you're on somewhere. It's only say in space. Floating weightlessly in space. So here is shaking requires some effort, but less than on Earth, because the wrench weighs less in space. That's wrong. And the weight again depends on the gravity. Now we're in space. And so if we eliminate this, the answer C is very easy before even we read it. So when you read it, the shaking requires the same amount of effort as on Earth, and that is true because the inertial mass of the wrench is the same no matter the wrench location, whether it is in space or it is on the Earth. Your wrench has the same, because your mass, the mass of the wrench, okay, it doesn't really change. So here is your wrench right there, no matter the wrench's location, whether it's in the space or on the Earth. So here your force is the mass and acceleration. Your mass is your moment, inertia, and then here is, of course, your angle. So know that in space your weight is zero, is because your weight depends on, so when you look at it, the weight depends on the gravity, and you don't have it, so the weight is nearly zero. The gravity is very, very small, nearly zero in space. And then you have the mass of the wrench is going to be the same, doesn't matter in the space or on Earth or on Moon. And of course, this is just telling you the sum of your mass. So this is moment of inertia, is how we usually defined it. So if you want to know, what is this, we just identify, is this little, see this little sign right there, the symbol, I'm just telling you it's a sum, all of it. So you add everything. So here we call it the moment of inertia, is because the moments or torque, right, adding on that body, which is this guy right there, is your moment of inertia, which is this guy, okay, and then your angular acceleration, okay. So pretty much this and this is about the same. So here we describe the moment, and here we describe the force here, in terms of mass and acceleration, and here in terms of, okay, the moment of inertia, and then of course the angular acceleration. Okay, so that's, we're getting into the rotational. I would just write it here, rotational, okay, dynamics. And this is what we familiar, your force, mass, and acceleration. So it's just showing you your linear and the rotational, dynamics. So linear is something that you are comfortable doing it, because a lot of the education, courses is gonna go with this, for you initially, and then of course as you study, you will get into more on the rotation, because not everything is going in a linear one axis, okay, dynamics or motion. So your motion is very, very complex. You translate, rotate at the same time. You rotate and rotate at the same time, or translation, or numbers of translation and rotations are happening at the same time. So going into the relative motions, Of course, even if you don't understand, but you do understand, okay, at the same time, you think like you don't understand, but actually you do understand, because you're born with those motions, subjected on you, because you're going in a motion on the Earth, and then your Earth is again in motion, and that Earth is, okay, having a two major motion, spinning on its own, and also orbiting. I will call it orbiting, okay. And then of course the entire galaxy is also moving, not only our solar system is moving, but the entire galaxy our solar system is in is also moving. So if you think about the motion, the axis of motion, the relativity is very, very complex, yeah, and it is very difficult for us to be able to calculate accurately in that complexity. Okay, of course, and then we're going to get into force. So idea of your force is nothing but is acting. Okay, and let's just take a look at it here. Every time we think about the force, again, it is acting on something, so therefore it definitely contain the aspect of direction, yeah. And of course, every time we think about the force, there is associated motion happen to the mass, so therefore you have a location, position, yeah, and then the movement. So as soon as something moves, and here I'm just going to write it a mass. As soon as something moves, then you have a change of location or position, and the movement is going to go in a particular direction, yeah. So, and then of course we always have a unit, because every time we talked about a magnitude, we've got to define what, like what is the amount of it. So therefore we use a unit to describe that amount, yeah. So these are nothing but the measurements coming in. So we have your Newton, and then your pound depends on the unit system, and this is our US customary system. The name has changed to US customary system because we want to ditch the word English or British, yeah. So anyway, and then of course a Newton is a Newton, our founding fathers American, yeah, unit. So anyway, so here is your table, and then of course you have your weight is your mass and acceleration, yes. And you must always understand your weight is your force. Of course, here we are describing the mass as an apple here, yeah. And then of course here is the center, meaning like it is going down towards that core, okay. And of course you also have another force, okay, and that is acting on this situation where the apple is sitting on a table, yeah. In order for this equilibrium to happen, for that apple to sit on the table, you need two forces that are balancing each other, yeah, in that equilibrium. So when you take a look at it, the weight of this, okay, apple, yeah, and the force that is exerted on that okay, apple by, all right, by the table is going to be called the normal force, okay. Is usually normal is because it's 90 degree to the ground or the reference, all right. This is kind of like a reference plane, because you have a force in that direction and you have a weight, okay, in the opposite direction that are in balance, okay. So therefore this placement of the apple on the table can be successful, okay. So we're seeing actually the resultant force, yeah, which is keeping the apple on the table, all right. And again, of course, don't forget this thing is happening on the earth, right, subjected to again the gravity of the earth, and then that earth is again in a motion again, yeah, on its own, spinning and then orbiting, okay, and so so everything got to be in your head before you understand what's going on here on the earth. Then we get into acceleration, review a little bit about it because they are aspects of motion. So then here, how do you know when you are moving? Okay, of course you know if you are a human. When you move, you definitely know you're moving or you're not moving if your brain is working, yeah, perfectly. So you know you're moving when you feel as a human, yeah, a force. But for object, it doesn't have a nervous system to feel it, but they do have a particle instinct or particle knowledge. We call it particle knowledge, okay? Meaning like they know what they're doing. It's just a chemical attraction or particle attraction Yeah, they love to aggregate. And then I told you so many times again, particle love to aggregate to make form. Yeah. So we don't know whether the particles are living or you are living. You actually are just living in a system state. Okay, you are already a system. This is a particle state. Okay, I just say state because life is a state, a living state. So here is we call it non-living from the human perspective. We have no idea what kind of knowledge this particle has. You know how many lives or years or lives that this particle has ever lived in the same space, which is our universe or multiverses. In fact, they're older than us because they are older, yeah, because the smaller the particle, the longer they exist in the space. And we are big, yeah, so if we are big, our system is breakable. Why? Because of the forces acting on it, and these forces are generated by the environment or the medium, okay, this system is in, and you are one of the system in the environment. Okay, it's just a living system, so you talk and you feel and you can do a lot of the things. So that the system capability us is better than animals and plants right now. Yeah. Okay. So anyway, that's where we are. Yeah. So anyway, and then of course we are going to take a look at the force and then the acceleration and then the mass very, very carefully. Yeah. And then we see this, yeah. So the force is a summation, meaning like there are many different kinds of force acting on something, yeah, acting on this mass. This mass is not being acted by a single force. There are many different forces acting on a mass, okay? And because of the sum of that force, this mass is going in a motion, having this acceleration, okay? So that's what you really, really need to get it. When you think about the acceleration, you know that there's a physical thing behind it, okay? And that physical thing is moving with a lot of the forces acting on it, okay? And it is moving with going from position to position, having a velocity, and the velocity changes, having an acceleration, meaning like I am moving, I'm taking position, I'm having a velocity, and I do have either constant acceleration, average acceleration, or instantaneous acceleration of some type with me. Okay? So if you think about it physically, you have only that mass. Okay? Condition moving. More conditions subjected to many different forces. And you can add them up and you've got that. Okay? And it is moving with acceleration because you have a velocity. Why? Because you are changing position to position in the space. Okay, so these are everything you have to know as soon as you think about the force and an object in a motion. Okay, and acceleration and velocity and change of position in a particular time. Okay, got to come into your head very automatically. Okay. Alright, I try to stop this lecture recording about 1 hour here. So we have a couple of minutes and we can get into this particle Newtonian mechanics. Yeah? And we will get into, yes, the next one. Okay? We will get into Newtonian's law. Yeah? So the very first one is, let me go back to the first slide. And here we come into particle Newtonian mechanics, and we go into Newtonian mechanics, yeah, and then we get to Newtonian laws, okay? All right, so the very first law. These laws are found by this guy, Newton. Therefore, we gave him, okay, credit, his name. And of course, I have already, told you about this. You recall, go all the way back to the ancient scientists, yeah, when we were talking about mass and weight, yeah, the difference between mass and the weight. You put an object into the liquid's container. Let's just say, like, as soon as you put a weight, the water will spill. The amount of water is equal to, the weight of that object that you just threw into the container. So anyway, this is just telling you, go and watch the video. The video, you can type this in, okay? I gotta tell you all the time how to do it. It's just so like depressing to understand that today students, because if you don't tell them step by step, they don't do anything, and I'm just having an issue with that. Yeah. So if you see this, you should know that I'm gonna just go to YouTube and then I'm gonna punch this in our short video, and it should the thousands of stuff will come out, and you can look that up. Okay. I shouldn't be saying that. You should be having your own common sense to be able to do these things because you are over 18 years old. Okay. And I have no idea why I have to show you everything like one by one. Okay. That's not fair, yes, to the professors. So make sure that you put effort and do these things by yourself. Okay, we're not in high school anymore. I'm not gonna go to the YouTube and then type in. Even that, I do it for you sometimes. Okay, so you're gonna watch the inertia video. Okay, for this example, of course, 1 minute and 22. Okay, a second meaning for this particular video. So if you just copy this or go to YouTube, you should get that video for you. Okay, and it is, like we have, of course, this textbook is a little bit old, so right now we have even newer videos up on YouTube, so you can watch one of them. See, like, where, let me just stop here for a while, and I am doing this for you again. Okay, so this is what we're talking about. So make sure that you go inertia, mass, speed, gravity, work, acceleration, 1, 2, weight versus mass and kinetic energy. Okay, make sure that you watch this, and you can find this video very, very easily. If you cannot find it, I'm going to be like having an issue with you. Yes. And then, of course, we will get into something called the motion. Aristotle, ancient, again, scientist. So he believed that if two objects, okay, and they have different mass, all right, I'm just going to draw mass 1, and then, of course, this is mass 2. They were dropped, okay, at the same time. You're going to drop it from the same height at the same time. So the heavier one, okay, is going to hit the ground first. So that's what this person, long time ago, this guy, okay, believe. And it is not true, okay. And another guy came up, and so his name is Galileo, and it said no, okay. So he reasoned that it did not make any difference how heavy two objects were, and he said they would both fall, okay, at the same rate, regardless of their mass. And when the condition, if they were not acted upon by air resistance. Okay, so this air resistance, very, very important. So when you think about your Earth, you know that we have an atmosphere, layers right there. Even the entire airplane can float on it, meaning like there's a distinct medium, and we call that the air resistance. Just like your water, okay, your airplane is actually floating on the mass of air. You have the mass, so we have a mass of ground, we have mass of water, and then we have mass of air. Okay, how heavy the air is on you, that's your pressure right there. When the air moves, then you can feel the wind. It can even get rid of the entire house, right, buildings. So think about it. So when hurricane came, we're so afraid of it. Tornadoes, right, afraid of them, because those are mass, right? They have incredible amount of particles in there, even though you can't see them because they're so small, just air. But it has force because it has a particular mass, and we call that air resistance. So if you get rid of this air resistance, doesn't matter what mass, all right, the small mass or big mass, and you release them, they're gonna drop at the same rate. So how they come down, whether a feather or a stone, it depends on the air resistance in that environment. Okay, so this air resistance, all right, is going to determine which object or which mass is going to come down fast, because you gotta look at the air like this. Okay, even though you can't see it in your brain, you should be able to see the particle like that is a medium. And of course, if you put a feather or if you put a stone, stone has more mass. So it's going to go through that medium because it has a more force because your gravity is pulling you down. Yeah. Of course, the gravity also pull the feather down. Yeah. But this feather got to go through the little tiny particles in the air. Yeah. And it doesn't have a lot of force like the stone. Yeah. So therefore, this force is going to make it. You need the force to go through these little particles inside of the air, and we call that the resistance. All right. So your airplane can float, okay, on the air. By the way, as it you only need to increase the number of the particle by going to a particular altitude. We call it height. So if this guy, if the airplane has a bigger mass, then you gotta go higher, to increase the cushion that it needs to float on. Okay. So anyway, so this air resistance is going to lift this weight up. So make sure that you understand that air has a resistance because air is composed of many little tiny particles, and they have a pretty physical. They are very physical. It's just that you can't see them physical, and they can be able to lift many objects on it. Depends on the amount of the air at that region and the size or the mass of your objects. Okay, so if you get rid of the entire air resistance, all right, just a pure force of the gravity, they're going to come down at the same rate. Okay, because of the same acceleration. All right, so the first law, Newton, he took Galileo's idea and then he summarized it and put it into a law because this guy didn't do it. So the object, okay, at rest meaning it's not moving, okay, tends to stay at rest. Okay, no moving object is going to stay just there. It won't go because there's no force which is going to disturb that balance to stay at rest. Okay, but if you do have a force, it would definitely get rid of the balance and it will move. So an object in motion, okay, is going to stay in motion and it's going to go with a constant speed. In again, this arrow is showing you straight line. So here this is a cartoon for Newton. And so object at rest is going to stay at rest. Object in motion is going to stay in motion on a straight line, okay, with a constant speed is his first law. Okay. All right, the second one, before we go into second one, we're still on the first one. So here we put it systematically together in a meaningful sentence. A particle at rest. See, now we call the object with a little smaller particle. So particle at rest or moving in a straight line with a constant speed. Again, they can do it because they are in equilibrium, and that equilibrium is not being disturbed by other external force. Okay, so something that is staying will stay, something that is moving will move as long as they are in that state or equilibrium. They can do that because they are supported to be in motion. They're supported to be at rest in that region or in that location in the environment. Okay, so if you change the environment, if you change the location, then you're going to have a different forces acting on it, so the equilibrium might be maintained or it might be disturbed. Okay, so what is equilibrium? You need to know that because equilibrium, we think about a particle is in equilibrium. Okay, the condition is if it remains in its current state without adding or eliminating forces. Okay, so if you have extra forces, that equilibrium will be broken. If you get rid of the forces from the equilibrium will be broken again. So therefore, don't touch anything in the equilibrium. If you add it or subtract it, your equilibrium will break. So here we define the equilibrium like this, meaning we do not have any external forces, okay, on that system. So therefore, a system at rest will be rest. A system in motion will be in that motion. Okay, they can afford to do that. Then we're going to give it a name, the Newton's first law, and we call it law of inertia, because something that is doing something want to be in that state, doesn't want to change. Like you comfort zone, don't want to do anything different. And me coming into your comfort zone and giving you all different things, and you have issue, adjusting yourself to me. Because people like people who do the same thing, okay, and people resist or go against the people who bring in a new method or new things to them, because they're not familiar to it. And I am notoriously famous for that, okay. But people like me always make new stuff, by the way, because our brain works that way, okay. We can see things that are missing in you or in a system. I don't like the same thing, and I don't know why. My brain got really bored, very very bored, and I need new challenges, and always make my own problem, and always make my own issue out of my own life. And my family knows about it. Everybody who work with me also know about it. But people like me are people who will make it or break it kind of person, who take a lot of risk. But I like to do it because every time you do it, you find something new, okay? Whether that new method works or not, you at least try it, okay? So make sure, I want you to be like, I want you to be in our group, okay? Who challenge the normality or something that's already existing. What if we do something else? What's going to happen? Are we going to fail, or we're gonna make it? Because if you don't do anything, it will be the same. If you failed, we just learn the method, okay? And so you can improve upon it. And if you are successful, well, we have a profit there. So don't be afraid to do different things in your life, because you need it, okay? You need it to keep the brain active. So what is inertia? Another word that you got to identify. Even though it is word, you should be able to explain it, okay? Inertia is the resistance to accelerations. Again, every time you think about acceleration, this thing gonna come into your head right away, okay? There's a force that is causing, the mass to move, and moving within acceleration, So inertia is something that is resisting, all right, to that, okay? So meaning like going to keep that condition as it is. So that's a tendency to keep the condition in the same way, or in the same way as it is, okay? So inertia is, again, it's just a resistant of the system, resistant to the motion. When we say acceleration, we're thinking about resistant to a motion. When we think about the motion, you gotta know that there's a freaking force behind it, okay? So resistant to external force, is inertia. Of course, what I'm gonna do is I'm gonna stop right here, and I'm gonna record another 1 hour, okay, lecture video for you. Yes. So let's close it, and I'm gonna continue from this slide in the next video.